2 successes or 3 successes or 4 successes, so on and so forth. So the binomial probability distribution is going to look like a histogram or like a bar chart, which is good and all, but that's a lot of work if we're going through every single time and having to look up a lot of information. So it's actually quicker in some instances to use the normal curve to approximate it. So the normal curve, our bell curve, that doesn't have just whole numbers. That's got every single possible number. So it's got this nice curve to it instead of being whole numbers like for the probability distribution. So this is the process of how to use the normal curve or a bell-shaped curve to approximate for binomial experiments. Okay. So as a reminder, the criteria for binomial probability experiment, this experiment is performed in independent times. Okay? So we have a fixed number of times that the experiment's done. So a fixed number of trials. For each trial, you're going to have 2 mutually exclusive outcomes. It's either going to be a success or a failure. The probability of success is the same for each trial, and they're independent. So the outcome of one trial does not impact the outcome of another trial. All right, so here's some histograms of binomial distributions where we have our n is changing, but our probability of success is 0.2. And hopefully what you start to notice is that the bigger this n is getting, the more normal this curve is looking. So we go from way skewed right to, well, kind of skewed right, but yeah, maybe a little, but maybe normal, to, yeah, that looks pretty normal. And the only difference between these 3 is that the n, the number of trials, is increasing. So we've got to figure out if using the normal curve, the normal distribution is appropriate. So the way to figure out if it's appropriate is to figure out if n times p times 1 minus p is greater than or equal to 10. So this will basically let you know, yeah, it's okay to use the normal distribution to approximate this. So this np onto 1 minus p greater than or equal to 10, this is going to determine if we can use the normal curve to approximate what we're looking for from a binomial experiment. All right, so once we determine that the binomial distribution is approximately normal, we can use the normal distribution to perform approximate calculations. Now I'm going to zoom in here, hopefully. Okay. All right, so down here, again, you just have these nice whole numbers. So this is for your binomial experiment. This is the number of successes. And then we have the normal curve on top of it. So if we were looking for 18 successes, well, if we had all this information already drawn out, we would just figure out the area of this little guy right here for 18, the existing rectangle. But we're using the curve, which means 18 is just a line. So just a line at 18 doesn't do us any good. So that line right there has no area. So what they do is if we want to find the probability that we're going to have 18 successes in our binomial experiment, and we're using the normal curve, we can't just do 18. So we're going to give it a width of 1. So we're going to go 0.5 above and 0.5 below. And if you look really closely up here, so 0.5 above is this line, and then the 0.5 below is right here. So we're not including this little tiny bit, but we are including this little tiny bit. So it kind of adds up to about the same thing. So it's a good approximation. So again, if we're just trying to find the area, or that we would have 18 successes, we need to go up and down by 0.5. So we're going to have a width of 1. All right, over here. So if we want to find the probability that x is less than or equal to 18. Again, whenever we were finding the 18, so whenever we were finding the 18 to begin with, we went from 17.5 to 18.5. Well, now we want everything less than 18, so we're going to include that top number and then go all the way back. So we're actually going to include that 18.5. So if we want to be less than or equal to 18, instead of us doing this from 18, we've got to bump up 0.5 and get to 18.5 and then figure out all the area underneath the curve. Just to point it out, having 18 or fewer successes, I could have also said the probability that x is less than 19. Because we're talking about binomial experiments, everything is in whole numbers, because we're only talking about the number of successes. So if I said less than 19, it has to be 18 or fewer. So one of the steps that I've put up here is to translate to approximate probability, and we're going to have less than or equal or greater than and equal signs. So if you have just a less than or just a greater than, you're going to have to translate it over to have the or equal. And if we have an equal sign, that's fine too. We're going to end up still translating that to have less than or equal signs. All right, so it should still feel a little weird, yeah? Okay, that's fine. It's allowed to for a little while. All right, so we're going to start talking about a little bit more. So again, if we want the probability of x equaling a number, x being the number of successes. Okay, so again, this is a probability of experiment. We're talking about the number of successes is what we're counting. So that's always going to be a whole number. So if it tells us that x equals a particular number, I'm just going to pick a random number 12. Then whenever we translate that over, from that 12, having just 12 is no area. Because again, we're looking for the area under the curve. So we're going to go half above and half below. So really what I want is the probability that x is between 12 and a half. So there's my half above, and then I need to go half below. So 11.5. So if we have the or equal, wherever our number happens to be, we're going to go half above and half below. So half above and half below, and then pretend those are straight. And then that's the area that we're actually looking for right there. So if we have the probability that x is less than or equal, so if I want the probability that x was less than or equal to 7, again, we can't just go from the 7 on down. We've got to bump it up and give it a little bit more area. So normally, so we have 7 over here. To find the area of just 7, we would have gone above and below by 0.5. So we would have ended up here at that 7.5 for just the 7. And if it wants everything less than, well, we're going to want this. We also want all this area here. So it's actually everything below the 7.5 that we would care about. So the translated probability is going to be that x is less than or equal to 7.5. For the greater than or equal, so probability that x is greater than or equal to, we'll go with 9. So again, we have our picture. Well, normally with 9, so we'll pretend like right here's 9. Bless you. We would go half above and half below. So we would have that 8.5 here, and then to 9.5, and that's if we were calculating the area for just 9. Well, it wants everything that's equal to and greater than 9. So we want not only the 9, which would have been this area to begin with, but also everything greater. So instead of it being the probability of x being greater than or equal to 9, it's going to be the probability that x is greater than or equal to 8.5. And then if it's going through and giving us two numbers, so perhaps, wow, hang on, let me fix that. There we go. So probability that maybe x is between 2 and 4, something like that. Well, again, normally, so at 2, and I'm going to go ahead and draw 4 in there too. At 2, we would go half above and half below to figure out 2. So that low point is going to be 1.5. And then for the 4, we're going to go half above and half below. So that high point is going to be 4.5. So we would want not only the area at 2 and the area at 4, but also all that stuff in between. But instead of using 2 and 4, because we're using the normal curve to approximate it, we're going to be using 1.5 and 4.5. So essentially what's happening is whatever our number is, if we have a, less than or equal or a greater than or equal symbol, if you go through and draw your line, or draw your picture. So for this one, the probability that x was less than or equal to 7. So if I go through, I get my nice little picture. I'll draw my 7. Less than would be this area. To go over and use the normal curve to approximate, I'm going to add and make this 0.5 bigger. So that was 7. So I'm going to add just a little 0.5. So there's going to be my 7.5 that I'm going to add. If I want to flip that around. So here, greater than or equal to 9. So if I have 9 over here, normally greater than or equal to 9 would just be this area, and we would be done. But because we're using the normal to approximate the binomial, I want to add 0.5. So I want to add area to it. So I need to drop down by 8.5. And if I have it in between numbers, I'm going to end up adding 0.5 both directions. So again, if I originally had 2 and 4, and I'm looking for the area in between, I would normally have this. But instead, I'm going to drop back a half and add a half this way and a half this way. So instead of it being 2, I'm going to have to drop down to 1.5. Instead of it being 4, I'm going to have to go up to 4.5. All right, let's go through and actually try one. I think the process might be a little bit easier than it sounds like it is. Okay, so we're going to set up the following probability statements. We're going to set them up. We might work through one or two of them. All right, so on-time flights, according to American Airlines, Flight 215 from Orlando to Los Angeles is on time 90% of the time. Randomly select 150 flights and use the normal approximation to the binomial to, and then for our first one, approximate the probability that exactly 130 flights are on time. Okay. So we have to figure out that it's a binomial experiment. Well, good news, it said it was. But if we weren't sure, there's 150 flights, so 150 trials. So N is set. The probability of success is 0.9. And if one flight's on time, that's not going to impact if another flight is on time whenever it's the same flight. So whenever we're talking about from Orlando to Los Angeles, they don't have those planes leaving every 5 minutes to where if one's a few minutes late, then the next one will be. So one's not going to impact the other. They're all going to be independent. So it wants us to approximate the probability that exactly 130 flights are on time. So what in terms of the binomial experiment, it wants the probability that x equals 130 flights. So the probability that X is exactly 130 flights. Well, we need to translate that over. So that 130, that's just one little tiny line. And one little tiny line is not going to do us any good. So we need to make it a width of 1. So we're going to go half above and half below. So what we're really interested in is the probability that, yeah, exactly, that X is going to be between the 129.5 and 130.5. All right, so we also need to know the mean. We need a mu, and we want to know the standard deviation, so we can do some of the other calculations in just a second. So I'm going to write that up over here, actually, because this will be the same for all parts of this problem. So the mean, or mu sub x, yeah, it's just NP, which is really nice. So N times P. So for us, yeah, so that 150 times 0.9, and what's that give us? Yeah. All right, so there's our mu sub x. And then we also want to do the standard deviation. So the standard deviation is the square root of N times P times 1 minus P. So that's going to be the square root. The N is what? It's 150. Right, I'm trying to make sure you guys are picking the 150, not the 130. The N is always in reference to all of the trials. X is the number of successes. So that 150 times that 0.9 times 1 minus 0.9. Let's see if I can squeeze that in there. Kinda. So we got the square root of 150 times 0.9 times, and it's 1 minus 0.9. I'm just going to put times 0.1. So I'm just going to simplify that a little bit. So 3.674234, blah, blah, blah. So we'll go 3.674. Sound good? We'll go out 3 places. So we will keep using this number and this number for all of the parts. Yes?
Just in case in a future example.
Oh, yeah. Definitely, yes. And that's actually would be a lot shorter, right? So instead of doing the 150 times 0.9, you already figured that part out, and it was 135. So if you do the 135 times and then the 1 minus p and take the square root, yeah, that's beautiful. Yeah. Good question. Yes? At least 3. Yeah. Correct. Yes. So if you round up, it depends how much, but like if you're rounding to like 1 or 2 decimal places, you're probably going to end up being a little bit off compared to us later on. Stay at least 3. Like a lot of times I'll go to like 4 or 5 just because it makes me feel better. So we're a little more accurate. Yeah. Yeah. Oh, this is already rounded. Yeah, this is already rounded. Yes, ma'am. Which part? Okay, so the square, so finding the standard deviation, it's just the formula, the square root of n times p times 1 minus p. So all we're really doing is plugging in the information here. So it's just, so the square root, hang on. So square root, and then the n is going to be the number of trials. So for us, that's going to be the 150 flights. So we're just plugging those numbers in. So that 150, and then the probability of success, it's telling us they're on time 90% of the time. So taking that 90%, we're going to translate that to a decimal. And that's going to give us that 0.9. So I've got 150 times 0.9. And then the rest of it is this 1 minus p, or 1 minus that 0.9. So 1 minus 0.9. So whenever we calculate all this, so just literally just throwing this into the calculator, it's going to give us this 3.674. Are you clear on what the N and the P are? Okay. The other part is just knowing this formula. Thus, that the standard deviation is going to be the N times P times 1 minus P. So that's a new formula for us. I just kind of threw it in there at you. Why are we doing all this stuff? Okay, so the binomial experiment, it's going to have whole numbers. So the binomial experiment, if we do a binomial experiment, the results are these little bars. Well, instead of us having to go through and recalculate every single thing here, we can use the normal curve to approximate it. So we'll just get kind of close using the normal curve. And the normal curve, we've got all kinds of tables for, right? We're already using the Z table. We'll end up getting more tables. So what we're doing is we're trying to take something that would be very different all the time, so the binomial experiment, and using information that we already have readily available, so that normal curve information, to get a good approximation, basically. All right, so we're to here. So we've got that. So we went from it asking us the probability that exactly 130 flights are on time, so that x equals 130. So we've translated that. So we're going to use that it's that x is between the 129.5 and 130.5. Because again, equaling 130, that's just a line. We need an area. So we're going to have a width of 1 by going 0.5 above and 0.5 below. We're going to draw a quick little table. Sorry, a quick little just sketch. So for this one, I need a little bit of space. Pretend that's normal. 135 was our mean because we just figured that out. So there's our 135. And then we're interested in being between 129.5 and 130.5. So we're interested in the area down here. Correct? So there's our two numbers, and what we're interested in is this area here. Well, again, having these numbers is not super useful, but it's the step right before being useful. So we're going to do what we did before and make everything more standard by using z-scores. So we're going to take these and translate them over to z-scores. So as a friendly reminder, if I can find some space on here to write it somewhere. All right, we'll go up here somewhere. So z-scores. Your z-score is your data point minus, over. Look at you guys not forgetting stuff. Thank you. Yeah, so the data point minus the mean over the standard deviation. So we're going to come back down, and this is where it's going to look kind of horrible, but it's really just a calculation. So instead of us having the probability that x is between the 129.5 and 130.5, to translate that over to a z-score, we got to do the calculation. So we got the probability, and so the first data point is that 129.5. So 129.5 minus the mean of 135 over the standard deviation of 3.674. So negative 1.59. Thank you. Oh, just 5. All right, and then for our second z-score, we're just going to do the same thing, but instead of the 129.5, we're going to do 130.5. So 130.5 minus the 135 all over 3.674. All right. So do these z-scores make sense that they're negative? Did we expect them to be negative? Yeah, because they're to the left of the mean. So we're expecting them to be negative. So for that 129.5, we got a negative 1.5. So negative 1.5 for that z-score. And negative 1.22 for this one. Let me make that so you can read it a little better. And remember, your mean, what's the z-score at the mean? 0. Z-score at the mean is always going to be 0 because that's your smack in the middle. And to the left of it will be negative, and to the right of it will be positive. Okay, so we're getting there. To find the area of that little teeny red sliver, now we need to look up the area whenever we have a z-score of negative 1.22, and look up the area whenever we have a z-score of negative 1.5. Which I think there's a good chance I forgot my z-tables, so I will be very dependent on you today. All right, so the area for the negative 1.5, is that the one you gave me first? 0.066, I'm getting an 8.
Do we have to subtract the number?
We're going to end up subtracting. Correct, yes. So negative 1.5. We get at this area here is 0. And then the area all the way to that 1.22. Okay, so that area 0.112. 3 ones. All right, there we go. Okay, and then to find that little red sliver, we're going to do what? Subtract, yes. Because that 0.1112 is this whole area. That 0.668 is just this little bit. So we got that whole thing minus the tail we don't care about. It's going to give us the red part. So we got the 0.1112 minus that 0.0668. And that's going to give us all right, so it's going to give us that 0.0444. So all that to figure out the probability of having exactly 130 flights on time, it's going to be that 0.0444. Yes?
The order in which we subtract them, you want that the result will have positive or will be negative?
You're always going to have positive area. So remember, whenever you're figuring out the probability of something, you're actually determining the area under the curve. So anytime you're doing a probability, it has to be positive. So if you subtract them backwards and get a negative, look at it again and make sure that you get a positive answer.
So because we have the minus 0.5 first and then the minus 0.22, so it doesn't matter. Always put the bigger on top and subtract them and second.
Yeah.
Okay.
Yeah. All right, for part 2, so we're not going to go through we'll go through part of it. The part 1 is the worst part. Part 2 is going to be actually fairly quick because we've done most of the work already. So for part 2, approximate the probability that at least 130 flights are on time. At least, what symbol is that?
Greater than or equal to.
Correct. So greater than or equal to 130. All right, so this is good, but it's still not quite right for as far as the translating to an approximate probability. So even though it has the or equal, we're not done. So really, and maybe I'll draw the picture first. How about that? So greater than or equal to 130. If the 130 is here, and the greater than is all this area, I need to add a half to that area. So instead of being here at this 130, I'm going to have to bump back to 129.5. So I'm increasing the area by a half. So really, I want the probability that x is greater than or equal to 129.5. Is that okay? All right. So this is where it gets easier because of all the work we did on that first part. So we can go through this 129.5. We did the work here, and we know that's a negative 1.5 z-score. So I can go ahead and say, well, we want the probability of our z being greater than or equal to negative 1.5. Again, so we've got this negative 1.5 here. For our z-score, we want all this area. Whenever we looked it up, we got that this area was 0.0668. So, perfect. 1 minus that is going to give us what's on the other side of that line. So we're going to do 1 minus that 0.0668. Thank you. Is that okay? Yeah. All right, for number 3. So the probability that we have fewer than 125 flights. What symbol is fewer than? Yeah. So less than 125. That's the same thing. Well, hang on. So almost. So that's the same thing as less than or equal to 124 flights. Yeah, because you have to be strictly less than 125. Because it's a binomial experiment, it's only whole numbers. Less than 125 means 124 or fewer. So if we want this 124 or fewer, we're going to increase the area by 0.5. So we've got our nice little curve going. We've got the 124 would be here. We're looking at the area less than. So we're going to bump up the area by 0.5 and make that 124.5. So again, probability that x is less than or equal to 124.5. All right, I'm going to give you all a minute to translate this over to a z-score and then look up the area. I'm going to start it on number 3. So we knew that we need to figure out the probability of x being less than or equal to the 124.5. So to translate that over to a z-score, that's going to be the probability that our z is less than or equal to that 124.5 minus the mean of 135. And again, we figured that out at the very beginning. Divided by the standard deviation of 3.674. Thank you. So that gives us the probability that our z is less than or equal to, what's the z-score? All right, so the z-score being less than negative 2.876. This is a z-score of negative 2.86, negative 2.86. So let's see, now we looked that up, negative 2.86. Did you guys get 0.0021? Yes. Good. So not very probable. And we don't have to do anything to it, right? Because the area we looked up is the area to the left, and that's what we were after. All right, and then part 4. So part 4 is going to use part of the information we already have and then make us use a little bit of new information, I think. Yeah. All right, so we want to approximate the probability that between 125 and 135 flights inclusive are on time. So what that's meaning is it wants to include the endpoints. So we're thinking we want to find the probability that we are between 125 and 135 flights. But again, we need to translate that over. So we're thinking about our picture of being 125. And then 135 was our average, right? That was our mean. So that one's going to be right in the middle. Well, we want this area, but we need to add on 0.5 both directions. So really, we're figuring out the probability that x is going to be between what and what? And? Beautiful. All right, good. Good. But this is less useful, so we need to translate that over to z-scores. So we're going to look for the probability. So we're going to do the 124.5 minus the 135 minus the mean. Yes, that we do have. Thank you. So I actually am writing stuff I don't have to write. And less than or equal to x, less than or equal to, and then that 135.5 minus 135 over 3.674. And so that first one was at negative 2.86. So negative 2.86 that we figured out from last time. Less than or equal to x, less than or equal to, what's this one? So what is that? So the 135.5 minus 135 is just 0.5 divided by 3.674. Yes, so we're going to round it up to the 0.14. Perfect. I'm going to erase those numbers. We didn't actually use those. So we are looking at from 124.5 to 135.5. And those z-scores were that negative 2.86 and 0.14. Well, we already know that little area here is at 0.0021. We already looked it up. But this little area over here, so having a 0.14 for our z-score. Super, thank you. So this whole area is 0.5557. So we're just going to subtract the two to figure out what's actually in between. Because again, the area we're looking for is in between these two numbers.
How you get that 0.5?
Mm-hmm. Thank you. All right, is that okay? A little weird, but after you do it a few times, it's just a process.